welcome to another installment of the Data-Driven Ag series, sort of a combination of Plain Sciences Initiative, Integrated Digital Forestry Initiative, and Digital Ag. So this is the series coming up. I do this often. I'm Dennis Buckmaster in Ag and Biological Engineering. I serve as Dean's Fellow for Digital Ag, and I'm your moderator for today. But you're mainly interested in the presentation now today. And I did notice that Guang Lin put all of the keywords that are on the front of our mind in the title. So if this doesn't strike a chord or ring a bell, then you're not paying attention. I'll put it that way. So anyway, just a very little bit of background. Some of you would have heard Dr. Lin talk to us a couple of years ago when we had a session that was, what's the difference between data science consulting, statistical consulting, and the Purdue Ag Data Services. But we have him back today to talk about this particular topic, machine learning, that's trustworthy, etc. So just a little bit of background about Dr. Lin. He focuses on he runs the Predictive Modeling and Machine Learning Lab. And so his focus there is big data analysis with statistical machine learning, some predictive modeling and uncertainty quantification. Those of us involved with agriculture recognize that uncertainty quantification is a very important thing because of the noise in the data. He does some stochastic multi-scale modeling, and of particular interest to us, his applications are in the physical and biological realms, which is the world that we live in and breathe in. He is the director of the Data Science Consulting Service here at Purdue. He may talk about that a little bit. So anyway, thank you, Juan, for joining us today. Look forward to learning some new things from your presentation.
Yeah, thanks for Danny's introduction. So today I'm going to talk about the survey AI. So before my talk, first of all, I'm not an expert of agriculture. Okay, today I'm going to just talk about what I have done on the AI side, right, for the scientific engineering applications. Hopefully, it can inspire some collaborations, right, between you and me, so we can, develop some interesting stuff can be applied for the agricultural applications. So that's the goal of this talk. So in particular, so the AI I'm particularly doing is try to emphasize the interpretable, right, models, so that we can learn something from the data, can help us a better understanding of the physical models. That's the goal. And also, I want to quantify the uncertainty so that can ensure this model is trustworthy, so we can use that model to handle noisy data, can extract useful information from it. Also, I want this model to be robust enough so that if it give me a new set of data, can learn totally different things, right? That is not robust, right? We want this model to robust enough to handle noisy data inputs. Okay, so that's the goal of this talk. So first, let's talk about the 4 waves of AI. So this definition is not defined by me; it's defined by the DARPA. So they defined the 4 different waves, right? There's a first wave is from 70s to 90s, right? So one of the represent application is to play the chess, right? So using AI to play the chess. So you can see it's so this is one application. So for the second wave AI is between 2000 to present. Okay, so basically you will see like one using reinforcement learning to play the Go. Okay, this is the second wave of AI. Also Alexa, right? We use that to the speaker. We order them to turn on the light, turn off the light, other kind of applications. Okay, and then we're looking for like third and the fourth wave of AI. Okay, that we want are able to do excellent at perceiving and the learning and the reasoning, right? On the third wave and the fourth wave AI, we want to be able to perform any intellectual task that a human can do, right? So with the large language model like ChatGPT, right, that give us some opportunity that we can adopt the ChatGPT, right, help us to perform some tasks, right? So we can using large language model to training for some particular applications, right? For one example, so you can train so that we can replace the customer service, right, using the ChatGPT instead. Okay, so that's Of course, for scientific, there's a lot of kind of applications we can use here, right? One example is we can enhance teaching, right? So we're using the ChatGPT to help us on teaching, to help the students, right? To, so that their learning curve will be flatter, they can easily to learn stuff, right? So there's a lot of kind of application we can use. Let's look at some applications. So this is one of the applications using AI for image coloring, right? So we have a lot of old pictures, right? It's black and white. So we can utilize them to do some coloring so that automatically, so you don't have to do it manually, right? So that's what the AI can do, okay? So we can recycle some old black and white picture, make them colorful, right? So this is one of applications, we can utilize them. So this is another example. We're using the artificial intelligence such as AlphaGo, right? So basically using the reinforcement learning to using the machine learning against the human being, right? So that's another kind of application, okay? But the reinforcement has many different applications, right? Can be used for agriculture as well, right? We can use that to dynamical controlling, okay, to control the growth of the plants, okay? So that's another application. So this is autonomous driving. So we can using artificial intelligence to do autonomous driving, right? So if you have Tesla, so you already can utilize this kind of applications. So that's basically we just need to follow the car that have camera in the front, and then use AI to drive it to follow the lane. So that make sure your car don't go out of the driveways, right? So that's the one for applications. So we can utilize. So I want to also talk a little bit about the data science consulting service, so that we offer at Purdue, right? So this is supported by the College of Science, but we can help across the whole campus. Okay, so if you have some some data science related, you have some data you don't know how to analyze, you can talk to me, so I can help you on that kind of applications. Okay. So this is a part of the Purdue Integrated Data Science Initiative. So our consulting basically support the machine learning, like big data analysis, and some business analytics, right, to help you on design challenge in research, education, and business. So we can provide hands-on consulting support for machine learning and big data, and also we can provide a unique end-to-end consulting service. Okay, can work with you closely on like proposals, data analysis, visualization, and also we can help you organize, workshops. Also on the education side, we work with Impact program to help the faculty to incorporate the data science module into your courses, right? So I think with the ChatGPT of this, right? So that will be even make it much easier for us. Okay. Also, it's gonna help the workforce development, right? So our students, we want them to have the capability of doing the data science analysis techniques, also programming, right? So on the student training side, so we basically are training our students with real world data and the science projects. So that's what we are doing. So our mission is try to establish using the data science consulting for research education and industry clients. And we try to provide the self-sustained efficient data science consulting. And also we try to provide a data science focal point for federal, state, and the private sectors to engage. And also we can work together, right? It's basically, it's a consulting platform, right? So we work with the industry, right? The industry want to have different expertise, right? So they want to team up together, right, to offer a unified service, right? Cover different kind of expertise. So therefore, I think that will be important, right? Especially when we work with industry clients. So this is basically the expertise we have, so we can provide hands-on consulting service, data management, and also the data processing. Okay, and so we can handle like a database, right, and also the big data analysis, methodology for data science, text exploration, and the high performance data processing, and also the grant proposal manuscript preparation too. So this is a data science. So on the training education side, we train the students with real world data and through the consulting service. And then we have the vertical integrated this platform so that we can integrate senior graduate students and the undergrad students together to train them for data science training. And also we train students with large scale GPU clusters so that they can handle big data analysis for high performance data processing. And also we're training students, right, so that they could have integrated skills so they can do data analytic visualization, presentation, and the writing skills. Okay. So finally is we work with other faculty to build a data science learning community at Purdue here. Okay, so that's the goal here. So let's look at some application with the agriculture perspective and the forest. So this one application. So I work with the Professor Robert. So basically, we try to do the image classification work. So because we know across Indiana we have this white-tailed deers, right? In the back we have the golf course, right? If you will see some white-tailed deers there too, right? Especially if it's a snow day, you will see them, have better chance to see them. So, but the one thing we want to know is what's the population density across the whole Indiana, right, of the white-tailed deers. Why it matters? Because it's related to the deer management. So we want to understand the distributions of the white-tailed deers so that because it has an important ecological and ecological social impact for Indiana, right? So this project tries to develop a machine learning model to classify white-tailed deer from photos and estimate the population, the density of white-tailed deers. So what we do is we put thousands of cameras across Indiana as a motion camera, right? So that we put there for a season, then collect them back. The picture will be typical like this, okay? Then we use machine learning tool try to recognize, whether it is white-tailed deers, right? How many white-tailed deers there in the picture, right? At different locations, right? So that way we can count at different locations how many deers are there. Okay, this is very similar to when you do autonomous driving, right? You have camera in the front, then you want to say in front of you whether it's a person or it's obstacles, this type of image recognition. Okay, but it's a little bit challenge because if you saw here, you have very complex like the woods, right, forest there, like background, right? And sometimes you have a deer far away, right? You only see part of it, right? And you want to recognize this is a deer, right? Not a horse or something else, right? So it makes it harder to do the machine learning, right? So also think about like for human, you already have tons of like ImageNet, you have a tons of the database there you can use, right? For deer, it's not that obvious. You don't have that much resource for you to train your machine learning model, right? So therefore, also you think about like a Facebook, right? They can hire a lot of people to do the mark of, okay, this is a human, this is not a human. So they can hire a lot of people to do this labor work, right? But for us, it's very hard for us to build up this kind of database to train machine learning. So there's a lot of challenge for us to dealing with this kind of project. So this is one application. So the second application we are doing is I work with also Professor Jingjing Liang, okay, from the Department of Forestry and the Natural Resource. So the work we are doing is try to develop some AI tools in digital forestry. Okay, so the goal is because there's a strong demand for global, consistent, and local relevant AI tools to predict the future forest days and years. So existing the forest growth model are incompatible and inconsistent for large-scale applications. So that's why we develop this climate-sensitive matrix model using random forest. Of course, you can use neural network. So to estimate, the tree diameter growth, the tree mortality, the standard recruitment, and consequently predict the population dynamic. So that's the goal. And so this model, okay, is also more accurate. So that can better than the traditional climate-sensitive matrix model. So that's we have publication, okay, on that published at ecological modeling. So this is the forestry. So I also developed another project. This is with Professor Mohit, right? This is in ABE department, okay. So we try to understand also, basically, we want to develop a previous model, right, for microbial growth communities, right? So it's either the only model, the death and the growth, okay, they are able to account for different shape of the growth curves. So we try to use AI, interpret AI. We want to have a physical model, right? Instead of think about the machine learning, people using the such as neural network is like black box, right? Model, you train, you start your data, you train a good neural network model, right? But that does not help you to learn science, right? It's a model, it's good. But however, you try another new data set, well, you have to retrain again, right? So you only rely on your network, right? You don't have any insight. Maybe the data has noise, you train a garbage model, right? So you didn't learn the science behind it, right? So the goal here is we try to learn a symbolic model, right? That has a science representation behind it. So that way it's more generalizable, right? So if you really learn a good model, you can put in the textbook. You can teach our next generation kids, right? So that's the goal. Okay, we want to do the interpret model. So that's why, so we're using this interpret AI tool to create a bacterial growth model so that can incorporate the different variables such as the growth, death, and leg and the tail phases. So we also developed a paper on this perspective. Okay. So this will give you some examples. And also another example is want to design the optimal control strategy for the Ebola outbreak. Okay, so we know the Ebola outbreak in West Africa, okay, is a very serious threat to global public. So we try to take using the machine learning and scientific analysis, try to analyze the data and develop the optimal strategy for controlling of the Ebola outbreak. Okay. So here's another applications I developed with the Professor Wen Jiang from Department of Biology. The goal is this cryo-EM imaging, right? So could you have this big facility requiring a couple, it cost a couple $1 million, right? So the idea is we're using this frozen of some imaging samples, right? We try to get these samples, right? The sample is pictures right here, right? The black and white, 2D, the sample is 3D, but when you took the image, it become black and white 2D samples, right? Your goal is to try to do a 3D reconstruction to find the molecule 3D structures, okay? So that's what will be involving the 3D reconstruction task, okay? So this is one challenge, you have to do 3D reconstruction. The second challenge is you think about is the molecule, right? Is they are in different positions. You think about human, right? You think like we are the human being in the planet, right? You think about one alien from another planet, right? You look at the down using telescope, look at the human. They want to find how the human looks like, but too far away, right? Then you're using camera to take some pictures. But our human with different gestures, right? We like this, we like that. We have different gestures, right? So how do you know, right, how the person looks like? Because the data is so noisy, just like we look at the microscope, right? The data is very noisy, but also the little molecules, they are kind of, we have many legs and tails, right? They were in different shape, right? So how do you recognize how many legs they have, right? How many tails they have, right? So they make it very complicated, right? So the goal is, how do you, with this, such kind of big noise, right? How do you reconstruct the particular molecule, how it looks like in the 3D, okay? So that's why become very challenging. So what we did is we try to using the GAN, right? So-called generalized adversarial networks. So the idea is we want to model the structure using this generator discriminator. So the idea is we're using some training set, right? Train a generative adversarial network. So we inject some random noise to the data so that we have generate a fake image, right? So then we have another discriminator can using that to give an output whether it's a real image or fake image, right? So we train this generated adversarial model so that it can generate a good quality of the images, okay? Then we can use this image to train, okay, over this large scale of data to predict biostructure, okay? So basically what I'm in my group was doing is try to integrate machine learning and the multi-scale modeling together. So machine learning gives us a good opportunity so that we can handle the multi-scale features and the complex system. The goal here, if you look at here, so I have one coordinate is from theory to model, right? So on the left bottom is a theory. So we developed a lot of theories, right? Agriculture also. So we also have a better understanding. We have some equations to model the physics, right? But on the other hand, in some area, we don't have a lot of theory, a lot of models for them, but we have data, right? So sometimes you are physics rich, so we have models, but in some area we are data rich, but we don't have a lot of theory, right? In that perspective, so we want to do something so that we can handle the wide spectrum of applications. So like agriculture, right? It's a multi-scale by nature, it is, right? So how do we handle them, right? We want to bridge the different scales, right? So each individual plant, then you do want to do like a farm level, a different level, right? You want to predict the yield, right? In general. So the idea is we want to bring the machine learning and the multi-scale modeling together so that we can handle different kind of scenarios and use them to predict like the yield of the agriculture. I will use example to explain it. So basically, we develop a so-called physical informed machine learning, right? So that we can incorporate physical model into the machine learning so that it can satisfy the physical law behind it. One of the bigger problems with machine learning currently is you don't exactly satisfy the physical law, right? Because like engineering application, for example, we have to satisfy mass conservation, momentum conservation, energy conservation, all these conservation laws, right? But if you use machine learning, none of them they really satisfy. Okay, it just looks like. Okay, so however, if you just look at like YouTube, you look at the feedback, right? Or this you want to suggest you some books, suggest you some like movies, that's okay, right? You don't have a big consequence, right? But however, if you want to use AI to really to do the financial transactions, right? You go to Wall Street, do all these financial business transactions, it will have a huge consequence, right? You don't want to be wrong, right? Also, if you want to apply to the biomedical applications, so you want to diagnose whether the person has cancer or not, it also has good, significant consequence, right? So therefore, you want to quantify the uncertainty, be able to, evaluate, trust it, right? So there's a lot of, so therefore we have developed a trustworthy AI behind it. So let's look at that. So my group was doing is one kind of applications. I try to develop an integral AI, try to discover the physical laws from the noisy data. So I'll give some examples. For example, the COVID-19 applications we applied to develop a COVID-19 model to predict the dynamic of the COVID-19. And another also, I'll give example I developed for the Alzheimer's disease model build up and the predictions. And another application I was doing is the uncertainty quantification for the reliable AI. I want to quantify the uncertainty, how much we should trust the model, how do we quantify the uncertainty of the model. So the third application I was doing is I try to do privacy preserving AI for learning data from distributed sensitive data. You think about it, right? One of the obstacles for the current application of AI is on the private sector. You think about each individual company, they have some data, right? But they never share with the other company because producing the data costs money, right? So another example is medical application. Think about like one hospital, they have some like a patient imaging of MRI data, right? And another hospital also owns some patient data as well, right? But hospital A and hospital B, they never share the patient data, right? Then, however, if we want to train a good AI model to can predict like a cancer based on the MRI imaging, you have to use a huge amount of data, right? But however, the private sector, they never share, they cannot share, right? They're against the law, right? So they cannot share. How do you deal with that? So one way is to do this, we develop tools called federated learning. The idea is hospital A never needed to share data with hospital B, right? So hospital A, they just train an AI model, right? Using the hospital A data, right? Then they just passing the parameters of the AI model to the hospital B, right? Then hospital B takes that parameters, then using the hospital B model, their data, that they train on their data, so they can get a better model. Okay, so that's the basic idea of the federated learning. So we can utilize this to train a model without sharing the data. Okay, so this is one of I think it's very critical, especially you're dealing with sensitive data, private data, so that if you want to learn a universal model from it. Another application I will do is AI for science applications. We try to use AI for material discoveries. And also, I work with the Impact Data Science program, so we developed this Impact Data Science education program there. So the following also, so our group developed different kind of AI architectures, try to handling different kind of situations. So one we developed so-called like a multi-fidelity AI model. So the idea is, in reality, we're producing data with different resolutions, right? Using different models, different instruments. How do you integrate all this data using different sensors, right? Different resolutions, right? Like remote sensing data, or you have individual tower, also measure the climate, right? You have all these different kind of sensors. How do you integrate all this data together, right? So that we can integrate them together as an input, right? So that give us a comprehensive understanding of the physics behind it. This is one application. So the other application I'm doing is so-called physical informed AI. The idea is instead of you have to write in your own models, your physical models, you can just input this physical model, can develop a neural network, certify all these physical models. So that we call physical informed AI. So that this developed a neural network certify the physical law behind it. And the students, they don't need to develop their own solvers, right? That can flatten the learning curve, can help students better learning the problems. Also, we develop so-called learning operators. So that way we can handle very high dimensional problems so that you treat the neural network like an operator, like you do the plus minus, these are operators, right? So that it can handle different kind of resolution of data, provided end-to-end mapping. Right. For example, you want to input the climate data. You want to predict what's the yield of this year. It's gonna be looks like, right? So your data could be different resolutions of you have remote sensing data could be like 128 times 128. Also could be 256 times 256. It's all you can use as an input, right? Because current traditional neural network, if 128 times 128, you have to use 128 times 8. Otherwise, it doesn't work, right? So we want to go beyond that, so we treat them as just an operator, right? Also, I developed this federated operator learning, so to handle the sensitive data. So one example I will try to give example is try to do the image processing, right? This is of course this application is we try to do the machine learning driven control system for like a 4D ultrasound for cardiac ultrasound applications. The idea is we take the 4-dimensional ultrasound data, right? Can you reconstruct the heart, how the heart beats, right? Based on the 4D ultrasound data. So our goal is we can use that to replace the MR data, right? The CT data, right? Because it's very expensive to do CT, right? Can we using this much cheaper ultrasound, right? Also, this has no radiation, right? So that's much safer, right? Compared to the MR, right? So this goal is, for example, I can take the CT data, yeah. So I can do some reconstruction. So this is the heart beeping. The blue color is outside of the heart. The red one's inside. Okay, so we can do the 3D, plus the time, the visualizations. So we can use that to do the reconstruction. Also visualize, predict if the patient has some disease. Okay, so that's kind of application I think it can help us to build up using a much cheaper way to predict of the cardiac disease. This is one application. So another application I want to talk about is to try to do interpret AI for science. In particular, I want to talk about the COVID-19 predictions. So I have 2 papers on that. So one is on the natural computational science. The other is in the class computational biology. So let's look at the COVID-19. So we all know that. So the COVID-19, so we want to make a better prediction. The reason is we all heard about that, right? The COVID-19 have this ICU bed, we want to look at, right? Like for example, here at Lafayette, we have how many ICU beds, right? We want to make sure, we want to predict how many beds we need, right? How many ICU beds? This is a resource, right? But in the meantime, you want to predict how many people gonna go to hospital, right? So make sure we have enough beds to cover them, right? So that's very important. Also ventilators, for example, right? All that are very important. So also, you guys all heard about flattening the curve, right? So you heard about that. That's the reason why you want to have a good model, right? So if you look at this curve, it's basically without protective measures. If a government does not do anything, the number of cases will be like this, right? So this is the dashed line will be the healthcare system capacity. If you go beyond the healthcare capacity, that means a lot of people are gonna die because you don't have the resource to take care of it. You don't have enough ventilators, right? So that's why it's very important that we can do some control to make sure the number of people get affected below this curve. But in the meantime, you don't want to have the measure is too strict, right? Because that will, first of all, gonna hurt the economy, right? So you want to just right below this threshold. But how do you do that, right? That will be the challenge. How do you accurately predict, right? So that will make it a very challenge. So to do that, that's why we want to using data science and AI to help us to improve the model predictive capability to enable new science discovery and make critical decision, right? Critical decision, basically you want to implement some control measures, right? So to do that, if you go just if you Google COVID-19 forecast hub, right, that you're gonna find out hundreds of models people developed, right? So you can contribute your own model too. So this is basically historical data, right? This is the way we want to make predictions, right? All these over 100 models, they can make a match with historical data exactly, right? Everybody did a perfect job. But if you ask them, right, to predict the next week, right? So this is what happened. Everybody predicted totally different, right? So that's because you easily can do overfitting, right? You can overfit the model, right? Exactly matching the historical data. But if you want them to make a future prediction, it becomes very challenging, right? That is because your model is not robust enough, right? It's not interpretable, right? It's not, so that's why I make it a very challenge. So therefore, why, so let's look at why it's so challenged to make a good COVID-19 prediction. The reason is, first of all, it's the model parameters are not, some parameters are not identifiable. So basically, you don't have enough data, right, to help you. So think about COVID-19. A lot of people, they don't even go to hospital. They even don't report, right, to the CDC. So you really don't know, right, the exactly how many people really get affected, right? So you don't have really accurate data. Also, the data-driven model should be constructed based on the available data input instead of, very general model. So also, the rigorous model is needed to provide guidance on the model development, model identifications. So therefore, we developed this framework, try to build up a data-driven model. The idea is we first look at which kind of data we have, right? Which events happening, right? We build a model based on the data, not just based on what we think, right? We build data on the model, the data we have. So we first do the data acquisition. Once we get data, we build up the model. But this model, I want to make sure all these model parameters are identifiable. Okay, identifiable. That's we use a mathematical rigorous analysis try to doing whether this parameter is identifiable using the data or not. Okay, if it's not, we're gonna go back to redo the model development. If yes, then I'm gonna continue doing the sensitivity analysis to identify which parameter is sensitive, right? Based on the data, I also do model calibration. Then I will do the model robustness analysis. Say, what if I add some noise to the data? I want to check whether this model is robust enough or not. If not, I will go back to redesign my model so that make sure my model is robust. Right? Once I go through all the steps, then I trust this model. I'm going to use this model to do a forecast with the answer qualification. So I have to go through a rigorous test, then finally use that to make prediction. Okay, so that's the step I want to follow here. So let's look at I want to using the New York City COVID-19 as a test case. So this is from the February 2020, right, to the end of that year. This is what happened in COVID-19 at New York City, what happened at the different events. Okay, so we collect all this data, and if you look at initially they have no control, right? In April they have the stay-at-home order, then they have the mask mandate in June, then they have do the reopening phase 1 to 4. Okay, then they have the indoor dining reopen in September because indoor dining reopen and the number of cases goes up, right? Then we also have the vaccine started at the middle of December. Okay, so this is what happened. You can say the stay-at-home order has significantly reduced the number of people get infected, but when you are reopening the indoor dining, the number goes up again. Okay, but you have to because eventually you don't hurt the business. So based on all this data, so basically from CDC we can collect this 4 kind of data. On the top left is number of daily cases. On the top right is the number of daily hospitalization. In the left is basically number of daily deaths. On the right is the vaccine. So remember, we have dose 1, dose 2 for Pfizer vaccine. So we have the number of people get injected. So we have dose 1, dose 2. So these are all the data you could have from the CDC at the New York City, right? This is all you have. You want to use that to build a interpretable model. Okay, so that's all you have. Okay, you want to use that build a model. So we build up this ecological model. So I highlight in green color, that's where you get the data. The IHD. I means infected, H means hospitalized, D means death. Okay, the R means recover, and then you have a quarantine phase in between. Okay, so you can say this is the original population. If you take the vaccine, you can come here to the recovery phase. Okay, so this is the model. Okay, so we have susceptible, exposed. Okay, the A means asymptomatic. It means although you are sick, but you don't feel it, right? So that's called asymptomatic. Okay, so we built this model, but however, there's a lot of parameters we don't know, right? For example, the transmission rate, the hospitalization rate, the death rate, all these parameters you don't know. So that's why you have to rely on the AI to help you. Okay, so we build all these models. Eventually will become an interpret model. So this model basically is differential equations, right? That will basically can evolve in time, can make predictions. So to do that, so that we can build a model so that we can make a prediction of the future number of cases. Okay, and then this is basically the vaccine injection, and then we can predict of the population. So here, the blue dot, basically the data we collect from the CDC, then we make a prediction with error bars. So this shaded area is the error bars. Okay, we have a basic confidence interval tells you, what's the variation of this number of people get infected in the next week. Okay, so that's one application can utilize these tools, so we can calibrate these parameters as a piecewise constant, so that it can change during different events. So basically, we'll assume as long as the government does not do any control, the parameter will stay constant, right? If there's a stay-at-home order, come out, then the parameter going to change. Okay, so that's why our parameter will change after every government event happening. Okay, so that's what we assume here. By doing that, we also try to apply using this model, data-driven model, try to help the government to do some data-driven control, right? One example we studied is because the reopening, right? They want to reopen the indoor dining, right? So one decision they want to make is they we want to reopen it in the February 14th, okay? Because that is Valentine's Day, okay? So, but they don't know whether this decision is right or not, right? So we want to use the model to help them make the decision. So that's why we run in the middle. We say, okay, you open the indoor dining on February 14th, right? But we also build another model. Say, what if we let this delay 1 month, right? We reopen the indoor dining on March 14th instead, right? In another scenario, we run, what if we just don't allow indoor dining, right? We run three different scenarios. Then we predict the number of people getting infected. Then we can let the government decide which one, right, is acceptable. They want to do a trade-off between the number of people infected and also the number of the don't hurt the economy, right? Because if you never open, of course the number will be small, but you're gonna hurt the economy, right? Indoor dining, right? But maybe you could have a trade-off. You reopen the indoor dining on March 14th instead. That's gonna significantly reduce the number of people getting infected, right? So that's the data-driven, the useful data-driven model, right? You can run different scenarios, right? You just predict how many people are gonna die, right? If you make this decision, right? Or if you run these scenarios, you can run different scenarios because the model is cheap, right? Once you have good model, you can just run different scenarios. Okay, then you make the right decision. What's the number of people die you can acceptable, right? It's you balance with the economy, right? So then you do a trade-off. At least you have something to rely on. I think that's what the digital model becomes useful. Okay, so also I want to talk about the physical informed neural network. The idea is you have on the left you have a rich physics, on the right you have a rich of the data, right? So our agricultural application also have these two different kinds of scenarios, right? So how can we utilize the model we already developed in the combined with the data together to make a better prediction? So that's the goal. So we want to develop a flexible computer tool to study like model uncertainty, also incorporate data and the different models together to infer some unknown model parameter and discover some unobserved physics. So that's the goal. So let's look at what this physical informed neural network really can do. Okay, the idea is it can help design different kind of models. So the idea is, for example, what I show you this epidemiology model, right? It's all just ODEs. You guys all know ODEs, right? But we can make the model more interesting, right? Such as I can develop an integer order model, and I also can develop a so-called time delay model, and also fraction order model. So the idea is COVID-19 in particular is just a time delay effect, right? Because once the government follows some policy, right, the number of people getting infected will not be just dramatically reduced. Obviously, there's some like 1 week delay, right? It will not that dramatically going to change, right? So that's why you have to use a time delay model instead of the differential model. Because differential model has to happen right away, right? But in reality, it has actually time delay. Okay, the fraction model is the similar things, right? So instead of using the integer model we learned from textbook, right? Why not you take a half differentiable, right? So that is just another model, so-called fraction order model. So let's also talk about this physical informed neural network, right, to help us to build a better model. So here's a basic idea how we develop a physical informed model. So here you assume it satisfies some equations, okay? Then this beta p, q, k, that's the model parameters, okay? So then you build for each parameter, you build them three-dimensional. Then you have the measure of the data. So here, this is the right-hand side is the loss function, okay? You use loss, you minimize this loss function to train your neural network. In your loss function, you have two parts. One part is just data, right? It's very easy to understand. Basically, your neural network prediction minus whatever data you collect, right? You square them, sum them up, and it will be small, right? The first assumption. The actual stuff is here. It's basically, you assume this model, right? If you move your model, everything to the left, it should be 0, ideally. But in reality, it's not, right? So you want to make sure this model output, the residual has to be small enough, right? Then your model is correct, otherwise your model is not correct, right? So this is my second loss function, right? So I add these two things together, minimize it so that I can get an interpretable ODE models. So that's the basic idea. So instead of I just purely build a neural network, right? I can do this, so I can learn an interpretable model using the neural network. But this interpretable model, you can use it for different kind of scenarios. So that is another way to utilize this physical informed model. So then we can use this model to evaluate the uncertainties around different scenarios to make data-driven predictions. So you even can infer some you observed physics. You also can infer the model parameters. Okay, so that's you also can generate different kind of models to evaluate which model have good prediction, which model does not have. Right, then you can pick the good model from a big family of models. Okay, so that's the basic idea. So here also another thing I want to introduce is so-called fraction order model, right? So what a really fraction model is instead of learn from the calculus, right? It's a first order derivative, that's it, right? But in the fraction order is you can take the half derivatives, okay? Or 3/4 derivatives, okay? So the idea is basically it is a differential integrating, okay? So basically this also try to model this memory effect. I think in agriculture, a lot of agricultural applications is really have the memory effect, right? Such as you watering the plant, it will not grow immediately, right? So you have some delays, right? So that's why I think it's better to model the biological using the fractional model instead of integer model, right? It's just a model, right? Just somewhat useful, right? All models are wrong, right? The famous code, right? So how do you develop a most flexible model, right, to best match the physics, right? This is our goal. So that's why we try to build a fraction order model, introducing the memory in the dynamic, so that we can learn the fraction order from the data. So that's the novelty of this work. Okay. So for example, if I want to show you is this basically shows the difference between the fraction order. This is like K1, it's 0.89, right, versus just 1. Okay, so you can see it has a memory effect so that it will not decay that fast because you have the memory, you're going to decay slowly, right? So you can learn this, the fraction order just using data. Okay. So that gives you the much more flexibilities, okay, of the model. Okay. So one example to show why the fractional model is effective. You think about we use range, right? The integer model is a fixed range, okay? You just use it. So, but the fractional model is it's a tunable range, right? You can fit the different size. You can just tune it based on the data. Whatever data you have, you can adjust it to find the right range for it. So that's why the fraction model is useful. Can give you the more flexibility of building up your model. So to summarize, so basically we employ this structure and the practical identifiability tool to study the model to evaluate whether they are identifiable or not based on the available data. And also we build up this general data-driven model, okay, to help us, and also using the physical informed neural network. The second part of my talk is we try to improve AI for science. I want to use the Alzheimer's disease prediction as an example. This is a work we published at Nature Digital Medicine. So as we all know, Alzheimer's disease is a very challenge, right? And people have developed many tools, but it's very difficult to predict because we really don't understand the physics behind it. Okay, so what we do is we using the biomarker, okay, for the Alzheimer's disease. Then we use that to build a data-driven model, try to understand the progression for each individual patient. We want to make a prediction. This also can be used for agriculture application. I just want to use that use this as an example. So also we want to develop a purely data-driven causal modeling, right, to predict the Alzheimer's disease biomarker progression. We want to understand also the causal population model, also the causal individual patient model. That's what we want to do, right? Also, you can do develop for each individual plant, right? You can predict the plant grows. If the plant gets sick, you want to know what caused it, right? Right. If you do this treatment, how it can affect the plant's growth, right? All these things you can using the similar technology to develop. So basically, for this one, we're using try to develop, but however, the data always noisy. Okay, so that's a big problem when you're dealing with reality. Okay, ideally always nice, but when you're dealing with reality, the data always very noisy. Look at this, right? This all these different color means that we get from the database. The data is very noisy, right? So we have to do some treatment to get rid of the noise, do some post processing, try to remove the noise. Then we are able to develop a framework. This is the framework we developed, right? The idea is we want to try to initialize a model. That model have many possibilities, right? Then we want to, using the data, try to learn a causal model from it. Then we can develop a population model, right? So this model will be best fit the whole family of the patients. Then from there, I want to study some sensitivity analysis to look at which parameter is sensitive to each individual patient. Then we call it this parameter called the personalized parameter. Then I can utilize each individual patient to tune of this personalized parameter so that I can get a personalized model. Then you may ask, why not you just using the data to train personalized model directly? Why you train population model? The reason is you don't have enough data, right? Because this patient only goes there hospital twice, right? You can only get 2 data sets. It's impossible to train a good model from it. So that's why you have to first train a population model, then you can train a personalized model, right? Then you're using this personalized model to make a prediction for this particular patient. So that's the goal. So this is the model. So this is A, beta, tau, and N, and C. They are 4 different biomarkers. Okay. Then we take the data, we can predict how this biomarker are going to progression in time. Okay. But what we get is order differential equations so that it is interpretable. Okay. And also these model parameters also we can for each individual patient we can define for this particular patient. So it's so that's this model could be serve as patient specific model. So this is the model. So we basically also can use this one to make predictions in different scenarios to make our population model prediction. So this is the four different biomarkers. We can, this X is the time. So basically, yeah, normalized time. So we can define how they progress in time. Okay, so this is the model. So here we basically develop this data-driven causal modeling framework to predict using the biomarker progressions. Similar technique you also can use it for plants, right? So you based on the plant biomarkers, right? Basically like how tall the plant is, right? What's the leaves, the size of these biomarkers, right? The phenotype or genotype, you can do this, right? Within the model, you can predict how they're gonna grow, right? So similar technique you can apply here, okay? And so we can develop this population model, and so also we develop this individual personalized model as well. So here's another application I developed for climate model. So here is we try to look at this. So let's look at the one application. Okay, so this is a Central American precipitation. It's rainfalls. Okay, we want to predict how many rainfall we're gonna get. Okay, like in the Midwest. So you can see this is a Gulf area, right? So this is the red color means the number of millimeter of precipitation per day. Okay, so the left is satellite data. Okay, on the top is the current climate model be able to predict how many rainfalls. Okay, in the bottom is we tuned the parameters so that we can have better model and make a better prediction. Okay, so how we can achieve that is by looking at the model parameters. So we have 5 different parameter control the convection, right, inside the model, basically the convection of the water cycle. Okay, so we tune this 5 different parameters using the satellite data try to tune this phi parameter so that we can achieve the better prediction. So you can see this optimized model is much better than using default parameter because that overpredict the precipitation, right? But if you compare these two, they still don't match exactly, right? The reason is although I tuned the parameter, right? But still, there's some physics missing there, okay? So this is the only thing you can do. You can match the parameter, but you cannot match the physics, right? So that's why we need an actual effort to try to closure this model to give input more physics behind it so that we can matching the observation data, okay? So this is so-called parametric uncertainty, and also there's a model uncertainty, okay? So although I tune to reduce the parameter uncertainty, but there's still the model uncertainty inside, okay? So that there's a difference between this, okay? So this, I just want to show you the model uncertainty is very important. So here is another one for the global, precipitation, okay? Using the global climate model. So you can see the left is observation, and the right is basically simulation. So this is that's three different convection. This is a deep convection, shallow convection, we call it split convection. It's total convection. Okay. If you observe here, this is a shallow convection in the Central Africa area, right? Here we have in the satellite data, but here we don't even have it. Okay. So that's why our model are not really captured physics. Okay. So what we do is we collect the important parameters. So there's 12 of the important parameters. So I define the lower bound, upper bound of the parameter. I try to tune these 12 parameters, right, to matching with the observation. So here is the basically this is the optimized. So in the tropic area, I can recover this precipitation. Okay, so you can see we really are able to, but just tuning the parameters, right, to improve the physics, to capture the physics. Okay, so this is just I want to present today. So I want to end my talk by a quote from Norbert Wiener, because I had worked with in the closest possible ways with physics and engineers. I knew that our data can never be precise. Thank you.
Any questions?
Go ahead.
So, what is the difference between interpretable models and physics-informed models?
Okay, so yeah, that's a very good question, right? So first of all, interpretable is I want to have a model that is symbolic. Basically, it's just like you learn from textbook, right? It's symbolic, have explicit representation of like derivatives or the variables, so you can write a formula, right? Just like you learn from the textbook, right? But it's just the parameter you learn from the data. So that is the interpretable model, right? Physically informed, the physically informed neural network, you think about this way, it's still a neural network, right? But you don't need the data. You just give me an equation, right? As long as you have equation, right? I can generate a predictor model, right? So that I satisfy that equation, I can make a prediction.
But isn't that equation based on physics anyway?
Yes. So this is a physical informed neural network application is you don't have a lot of data, but you have the theory, right? Because like we have a lot of equations, but you can utilize this equation, right? You can, by minimizing, you can build up the data, can generate from the equation. You can think that way.
Say that again. So we can generate the data from the equation?
Yeah, from the equation. So basically the data satisfy that equation. You can generate a lot of artificial data right from the satisfy this equation.
And for the interpretable one, how is that different?
Interpretable is you can write down explicitly how this interpretable is, I give you a model. I give you an equation. Right? Then the equation I learn from the data.
So what is artificial intelligence about the interpretable?
You learn a model from it. It's very important, right? Just like you think about Newton find the second law, right? So now we don't need Newton, right? The data will generate the second law for you, right? It is significant. I think it's significant, right?
Okay, we can talk more.
Yeah, we can talk about, yeah. we want to use in computer, right? Think about like you have ChatGPT, right? You say you're doing the agriculture, you say, hey, ChatGPT. So I have this data, I give it to you. Can you find a model for me? Then the ChatGPT give you a model.
My job is done.
I mean, yeah, that could be,
I phrased this situation a little bit like this. Like, there are a lot of equations that explain a lot of things.
Yeah.
To only go with data and uninterpretable artificial intelligence is to essentially ignore all of the science that's been done.
Yes.
Up to now.
Yeah.
Like we have a sense of the shapes of curves, etc. And now we can apply the data and the analytics, the AI, to find the parameters of the models, not necessarily to determine the models in the first instance.
Yes.
Right.
Yeah, I think so. Yeah.
Where we're at. Yeah, question.
Yeah, so going back a little bit earlier, your talk, you were giving kind of an off-the-cuff example at 2 hospitals, MRI data, right? Where hospital A trains a model on their MRI data, and they don't necessarily share their data with hospital B, but you're saying that basically they share the model they generated.
They share the model parameters.
So then hospital B gets that, and they sort of improve upon that with their own data by kind of improving that model with that, right?
Yeah.
Okay, so I see that happening a lot with like the LLMs that are coming out. For instance, like the Llama 2 that have published and stuff, and then Stanford took that, they quantized it, optimized it, et cetera, and then it comes out on Packer, right? But all these models have their biases that are built in, and those biases aren't necessarily obvious, right?
Mm-hmm.
So we're going forward. Some of these questions that we're going to have aren't really questions about further improving the model, but more like consensus of models.
Mm-hmm.
So if you have like hospital A and hospital B, maybe the path forward isn't to have hospital B improve its model or improve hospital A's model with its own data, but rather have 2 completely sort of independent expert views on the thing and have a consensus derived from that through more like a more straightforward things, right? The consensus operators and logic and stuff like that. So I'm very concerned going forward that we're going to lose like basically like lineage on these things going on that, and basically that almost like double counting our references going backwards, right?
Yeah.
But
Yeah.
anyway, that's
So, but if you think another way is the hospital A model, right, give to hospital B, that model at least better than you just randomly generated all the model parameters, then you're using model B data to train, right?
Yeah.
Definitely will be better than what I said that way, right? So also you think about if a hospital B have a data that is less noisy, right? So it can correct the bias, right? If hospital A has a very noisy data, you train a better model, right? But you can, if your model B from hospital B have better data, then you can correct the bias, right? Because your data could have less bias.
if the quantities of data underneath that are similar.
Are similar, yes.
Yeah.
Mm-hmm.
I also, by the way, I find the talk on the physics informed stuff like models absolutely agree with what you're also saying for Professor Buckmaster. Like that's a big area I haven't personally seen a lot of work in.
Mm-hmm.
So that's great advancement there. Thank you for your time.
Mm-hmm.
Your comments make me now more aware and thinking about this lineage notion of as we develop models to fully contextualize and reference it, like what all went into it, not just here it is, but what were the stages of the development that got you there. I think it's going to be more important going forward, because then, well, can I trust it? Because I would want to know what were all of its sources. The same that we would review literature and we might trust work done here a little bit more than work done there or whatever.
Right.
We would want the same thing in this model work.
Yeah. Mm-hmm.
Yeah.
Thank you so much for your very interesting presentation. So I have a question about the situation when the physics behind, for example, vector A and response variable is unknown. For example, the relationships can be either linear or quadratic or logarithmic. We don't know it yet, but in that case, how do you implement that in your modeling?
Yeah, so I think, so of course there's an assumption behind, right? So what we do is we encourage so-called sparsity, right? So basically you assume, right, like Einstein said, in nature, the model should be as simple as possible, right? So therefore, you basically, what we did, we have data, right? Like what you said, I don't know, it's linear, quadratic, or third order, whatever, right? You just assume the highest order you could assume, right? You say false order, right? Then I try to encourage sparsity of the model parameters, right? Try to minimize using so-called like comparison sensing, a lot of techniques you can use, okay? Then you minimize it so that you encourage basically zero coefficient, okay? So that if you learn a lot of parameters, although you assume false order, but you get out a lot of zero parameters, that false order will disappear, right? You may only have the second order left, right? So the data will decide, not you decide, data decide. I think that's called data-driven, right? Model learning. So we, just try to encourage it to learn as simple model as possible. What happens is actually because of the noise of the data, you're gonna learn a lot of garbage of the high order models, right? So this is what overfitting, right? So because of the noise, you learn sixth order, models, right? But if you use another set of data, it could become fifth order. Which one you trust, right? So that's what happens. The noise can affect your learning.
Just looking at the clock, let's thank Dr. Lin one more time. We can linger for more conversation. Feel free to leave without worry of